Welcome to Chemistry Wide. Today we will see basic concept of coordination chemistry. It is depending on the three theories. First one, valence bond theory. Second one, crystal field theory. Third one, molecular orbital theory. See, understanding the orbitals. Let's see. First one, we see s orbital. See here, this is s orbital. This shape is spherical, so we denoted s. First letter s. This is the nucleus. This is the z axis. This is x axis. This is y axis. And s orbital is spherical with the nucleus at its center. This is nucleus. Let's see p orbital. Next. See, this is p orbital. This shape is going to double shape. This has three types, that is p, z, py, p, z. Sorry, this is px, py and pz. See here, electron in a p orbital has equal probability of being in either of. This is probability of the electron either in off. Let's see d orbital. So we need d orbitals for very importantly, because all crystal field theory or R complex are depending on the d orbitals. See here, d orbitals going to 5 types. Here see this box, dxy, dyz, dxz, dx square, y square, dz square. This is 1, 2, 3, 4, 5 orbitals. These are 5 orbitals called degenerate. Degenerate means similar energy or even energies. Let's see first one, dxy. See here, this is the x axis, this is the y axis, this is the z axis. This is going to back on the board. Please just keep imagine yourself. These orbitals present at x y direction only, so this is called dxy. Here z axis along the point, just imagine yourself. Next, dyz. These orbitals present at yz direction only, so this is called dyz. Here x axis along the point. See here, this is x axis along the point. Please imagine yourself. It means this is going to inside the board. Third one, dxz. Here see, these orbitals present at xz direction only, so this is called dxz. Here y axis along the point. Just imagine yourself. Here y axis inside the board. See the important point. These 3 orbitals, they are lie in between of the axis. Please, this is important. Wait. Next, 4th orbitals, dx square, y square and fifth one dz square. Here this both orbital going to combine together and give the new orbital, that is dz square. See here, this dx square y square. See here, here see dz square small lobe, this is small lobe x orbital, this is the x orbital of this small lobe. Here the two z orbitals combined to form a big lobe. See here, this is big lobe because both are combined to them or together. See below the important word, this both orbitals they are lie on the axis. This is the very important point between the two different types of set of orbitals. Here dx square y square orbitals lie on along the x and y axis, and dz square orbitals lie on the along the z axis. Please note, there are not 5 orbitals, actually 6 orbitals. Let's see below how. See, first one dxy, dyz, dxz, dx square y square. Fifth one dy square z square. Sixth one dx square z square. These both are combined to give these two orbitals combined to form the dz square orbitals. Please keep it in mind. Next, now 3 of them lie between the axis. The 3 will be always repel together and will be attract together. Now we are going to talk about the tetrahedral and octahedral complexes only. See the example here, dxy, dyz, dxz, these 3 orbitals all are in the same between of the axis, so their energy will be similar, and the other 2 orbitals, that is dx square y square dz square, these both are on the axis, so their energy are quite similar. Here dxy, dyz, dxz, these 3 orbitals called triplet generate. Mulligan symbol, it is represented by T. This Mulligan symbol T will be T2G. This T2G represent triply degenerate of the dxy, dyz, dxz orbitals. Another 2 orbitals represented by Eg. Here Eg represents doubly degenerate of the dx square y square and dz square orbitals. Now let's understand about the axis. Let's take the cube structure. Here x, y, z axis inside the cube, so we should understand how ligands approach here. Please see the structure. Now let's see how the in octahedral complex how the ligands arranged here. At octahedral complex, see here, if we take the one octahedral complex, here see here, here metal is the central, this is a metal ion, and around the 6 ligands, 1 2 3 4 5 6 ligands, this is called octahedral complex. We have 2 sets of orbitals. Please remember, T2G between the axis, Eg on the axis. Please keep it in mind, This is a very important point. Here 5 d orbitals are degenerate. Now if ligands going to approach them, they will split into different types of states. Let's see below orbital diagram. See here, these 5 orbitals going to split dx square y square and dz square, dxy dyz dxz. This is going to split two types when ligand approach. Here 5 orbitals degenerate free ions. This is the free ions. Here G represent gerade. Gerade means even or inverse in German word. See here, these 2 orbitals on the axis, they will repel more. See here, this is Eg, this is T2G. This energy gap is called crystal field stabilization energy. See below. The crystal field stabilization energy represents delta O. O means octahedral. Again, let's see the separately the diagram. See here, these 5 d orbitals going to split two types, Eg, another one T2G. This value, see here, this value plus 3 by 5 delta O gives, this value is 0.6 delta O. Please note here, plus 3 by 5 denoted opposites of the T2G orbitals. This is 3 orbitals. This is between the value. This both between the value of the 5d orbitals. See here, at T2G minus 2 by 5 delta O, it is going to 0.4 delta O. See here, minus 2 by 5 denoted opposites of Eg orbitals. This is 2 orbitals. Please keep it in mind. If you any confused, read or watch again this video. Here we got crystal field stabilization energy between the Eg and T2G. Eg plus 3 by 5 delta 0 gives plus 0.6 delta O. At T2G minus 2 by 5 delta O gives minus 0.4 delta O. This is experimental value. This value for only octahedral complex. Let's see tetrahedral complex. See below. This is a tetrahedral complex. This is a metal ion in the center. 4 ligand around the central metal atom. Here 4 ligands going to approach the metal ion. All the ligands approach between them in all the axes. So those orbitals presented which are present between the axes, so they will repel more compared to the on the axis orbitals. See the orbital diagram. See, let's see orbital diagram. See, this is 5d orbitals, free ion. Here dxy, dyz, dxz orbitals between the axes, they will more repel because ligand when going to approach between the axis compared to dx square y square and dz square orbitals. See here, see the crystal field stabilization energy here at T2 plus 2 by 5 it gives 0.4 delta T. T means tetrahedral. Here did not mention G because tetrahedral complex spherical shape. Same thing here. Here see the value minus 3 by 5 delta T, it gives minus 0.6 delta T. These both are experimental value. Let's see below how to calculate delta T and delta O value. See here, delta T divided by delta O gives 4 by 6 square. Tetrahedral complex 4 orbitals and octahedral complex 6 orbitals, just square this both value. So we get delta T by delta O 4 by 9 or delta T equal 4 by 9 delta T. This is the formula. Please memorize this formula. Let's see one problem. Find out the crystal field stabilization energy for CO F6 3-. Let's see first one, find the oxidation state. Here oxidation state is plus 3 because X minus 6 equal to minus 3. Here X is cobalt. So we get plus 3 oxidation state. Next, find the electronic configuration. Cobalt, it is going to argon configuration 3d7 4s2. So cobalt plus 3 oxidation state electronic configuration is going to argon 3d6 4 0. This is 4 0. Here remove the 3 electron because cobalt loses their 3 electron. Splitting, see the splitting. Here see this orbital. So we get 6 electrons only. So fill the 6 electrons 1 2 3 4 5 1 2 3 4 5 6. It is going to split 2 sets. First one EG and second one T2G. See at EG there is fill the 1 and 2. Again fill the T2G 1 2 3 4. So totally 6 electrons. Here Eg value plus 3 by 5 delta O gives or equal plus 0.6 delta O. See here at T2G this value is minus 2 by 5 delta O equal minus 0.4 delta O. See the crystal field stabilization energy for this complex. Here 2 into 0.6 plus 4 minus 0.4. So we get 1.2 plus minus 1.6. So finally we get minus 0.4 delta O. This is the crystal field stabilization energy for this complex. Please subscribe our channel. We are making more videos. All are on the way. Thanking you all. Have a nice day.